Okay, we have finished discussing about how to implement the artificial neural network from scratch. Now, let's take a look at the more advanced neural network which have been provided by MATLAB in the toolbox there. So you just can go to your Google and search MATLAB shallow neural network. Okay, so of course previously they don't call it shallow neural network because of the deep learning recently. Then they try to differentiate between a deep neural network and shallow neural network. The one that we learned in this chapter is a shallow neural network. Okay, so but I don't call it shallow neural network at the beginning because I before deep learning become trending, they just call what we learned in this chapter as a artificial neural network and multi-layer perceptrons. It's actually, this one is a multi-layer perceptron, but in MATLAB they already call it a new name, which is shallow neural network. You just click this one, fit data. Okay, you just open this one. Okay, as for this one, I will make it as your second group activities, meaning that I will we will do the same as our previous activity, where I will give you the name that need to present by next week, and I will release the name by Sunday, next Sunday. Okay, so what the representer need to do is they need to explore this shallow neural networks, meaning that they have to present they have to present this one, how to implement the shallow neural network by using this neural network tools there, which is called as a neural fitting NF tools. Okay, I don't ask you to implement the code, because in MATLAB there's a two way to implement a neural network. One is by using the tools, which is called as a neural fitting apps there, which is this one, fitting apps. And another one, you can also write code just calling the built-in function inside MATLAB. Actually it's the same thing as using the tools, because later this tool will can be used to generate the code for you, and of course this tool is better for those who not good in programming. So that's why I ask you to explore these tools, then you can understand how to try to understand how to use it. Okay, so that's why in the presenter need to go through this documentation and try to run this code. Okay, of course there's a code there, you just can follow each and every step inside here, and then you explain. It's as simple as compared to the previous activity, because the previous activity you need to derive the equation, but this one I give you the manual. I ask you to explore by yourself. I will not teach how to use these tools, because this is the one that you need to use for the assignment given by Dr. Ting, I think. Yeah, because Dr. Ting give you some assignment. They want he want you to compare the result between the linear model and the neural network output there. So that kind of assignment you need to do in these tools. Okay, because this is the one that the can solve the real application. Okay, not the one that I teach before, which is using develop the code from scratch. That one is very bad neural network to implement in your assignment. Okay, you can see that still this is MLP, multi-layer perceptron. This is the layer number 1, this is layer number 2, this is layer number 3. Okay, the same things there. And then you can set how many neurons, how many at the hidden layer, how many neurons at the output layer. Then you just run, but you need to show to me that you managed to run the code, and you can explain this instruction, each and every instruction here, how to run this tools. So every presenter need to do that up until up until you can I think until step number up until here, finish step number 16. Okay, you need to present that in 15 to 20 minutes video. Hopefully it's 15 minutes, because I think most of the free apps, the limitation is that you need to have some short video. So even the YouTube, if you don't do some verification, you can only upload 15-minute video. So that's why 15 minutes is enough. Okay, if you drag, it should be maximum to 20 minutes. Okay, that is the assignment, and I just want to highlight on something. Forget about that. Before I close the discussion there, I want to highlight on some things there. Yep, this is the one that I want to highlight. As you can see that later when you explore this tool, you can see that one of the setting there before you run the code, that choose a training algorithms there. Okay, for training algorithms there, you will find out there's a, instead of this technique which is called Levenberg-Marquardt training algorithm, there's also another option. Actually, this is one of the example of advanced backpropagation algorithms as compared to that what we learned before, which is gradient descent. Okay, instead of gradient descent, the better way to optimize your W is by using the Levenberg-Marquardt algorithms. Okay, again, like I mentioned before, what we have covered before is not the practical or the one that can solve a real problem, because of several limitation. One of it is that we don't have a stopping criteria, while by using the MATLAB toolbox, MATLAB toolbox, they have their own stopping criteria, so they will not execute the coding up until the maximum epoch you have set. It will stop immediately when they find out the training accuracy is going too high, is going higher, and the validation accuracy is going down. Because once that happen, that is the algorithm is going towards overfitting. To avoid that, it will stop immediately before you achieve at the maximum epoch. That is happen at the MATLAB toolbox. Another second characteristic that make this MATLAB toolbox advanced as compared to the one that we learn is that this one, because what we learn, to update the W, you are using a gradient descent, which is the first order derivative based optimization. But this one, they are using a Levenberg-Marquardt optimization, where this is based on second order derivative, which is will update the W based on second order derivative. So this one I don't want to discuss detail about it, because they are using the more advanced mathematics, and even that's mathematics you don't learn in your foundation or matriculation. So your basic is not enough to learn this advanced technique. So you need to investigate more information on the fundamental mathematical side, so which is will not cover in in your syllabus, but I just want to show you actually, because you will get blur because you don't find any gradient descent in this in this option. Actually, you don't have any gradient descent because it's already absolute and not is a one of the oldest version which have many problems in try to find the optimum point, which is going towards to find the best W that can fit into your data, because this algorithm is better than that, the Levenberg-Marquardt. So I just want to show you that, okay, this is the explanation I get from this website. Okay, explain the what is a Levenberg-Marquardt optimization is look like, but it's still a back propagation. You can see that. Okay, okay, this is the just to show you the fundamental that we learned before, which is gradient descent. Okay, this is gradient descent. Okay, it's still a gradient descent algorithms. Okay, and in this website they use the word steppers descent algorithm. Actually, steppers descent algorithm is another name for another name for gradient descent. Actually, some people call gradient descent as a steppers descent algorithm. Okay, you can see it's based on first derivative. What is meaning by first order derivative? Okay, first order derivative is because you are doing a del E, del W, del E, del E, del W2 and so on. But for Levenberg-Marquardt here is based on second order derivative. Okay, you can see that. Okay, for gradient descent, once you finish, this is how you update the W. Okay, and this one is the updater itself is based on the first order derivative, which is this one. But for this Levenberg-Marquardt algorithm, as you can see, you need to know some fundamental on the Hessian metric and so on. But I just want to show you that at the end the updater is different. Okay, which is let's go to the updater. Where's the updater training step? Wait, yes, this is the updater for Levenberg-Marquardt algorithm. Okay, it's a little bit different from gradient descent because this J here is represent a Jacobian matrix. Okay, where the Jacobian matrix is calculated from the Hessian matrix, and if you see the Hessian matrix and Jacobian matrix is actually the okay, if you see the Jacobian matrix here, it's based on derivative. Okay, it's a first order derivative, and then even you can see, I think here, yeah, this one, you can see that in order for you to get all this thing, it's based on this one, which is a second order derivative. Of course, I don't want to go to explain everything. If you can see that to generate all the updater for this algorithm is based on this thing, which is a second order derivative. Okay, it's not just del E del W, is a del E to the power of the del to the power of E, means you need to do first order derivative 2 times to find the error that that represent the error which is contributed by each and every W. So that is what is defined as a Levenberg-Marquardt optimization, Okay, they use the different updater. It's not similar with the updater that we learn in gradient descent. Okay, and it's better than gradient descent.